Good afternoon to you all. You are welcome to our third presentation. Bond lengths. The length of a chemical bond decreases as the bond number increases. Therefore, double bonds are shorter than single bonds and triple bonds are shorter than double bonds. The implications are that the more relationships we have between two nearby atoms, when we have a single relationship, the kind of attachment, the kind of link between these two atoms is distant. When we have two relationships, say for example, like I said, if we take a bond to be a relationship, so the way one atom relates to the other, if it is by two bonds, then they become shorter. The distance between them gets closer and closer. They become closer to one another, the distance becomes shorter. Therefore, the bond lengths become shorter. For triple bonds, they are very, very short. The number of bonds formed by an atom can be predicted by the number of electrons that an atom needs to fill its valence shell electron, to fill its valence electron shell, the outermost orbital. Non-bonded electrons are normally not shared with any other atom, and these ones are said to be actually not participating. Any pair of electrons that does not participate in the formation of bonds but is found to be in the outermost orbital are referred to as lone pairs of electrons. The geometry of molecules. Chemical bonds determine the geometry of atoms. The shapes of small molecules depend on the number of atoms in the molecule and the angles between those atoms. The electrons in the bonds and the lone pairs of electrons surrounding an atom normally repel one another and arrange so that they are kept as far apart as possible. This implies that when we have any two bonds between an atom, the central atom, and the other atoms, the bonds tend to repel one another so that we have the angle between them as large as possible, because the more they get closer, the more the force of repulsion, whereas when they get far apart from one another, the less the force between them. So for a tetrahedron is a four-sided geometric solid in which each face is an equilateral triangle. When an atom adopts a tetrahedral geometry, the atom is positioned at the center of the tetrahedron, and its four bonds and all lone pairs of electrons point towards each of the four corners of the tetrahedron. Atoms in which we have a total of four bonds, or bonds and lone pairs, normally adopt tetrahedral geometry as shown in the diagram there, or in the drawing which is labeled A. This geometry maximizes the distance between electrons in each of the four substituents. If the tetrahedral geometry is perfectly symmetric, the angle between any two bonds made to the same central atom is 109.5 109.5 degrees. This is exactly what we see when carbon forms 4 bonds. An example is in methane, where carbon is bonded to 4 hydrogens. The bond angles are 109.5 degrees. Atoms with a total of 3 bonds and/or lone pairs adopt a trigonoplanar geometry in which all 3 substituents and the central atom lie in the same plane, with the substituents at the maximum distance from each other. Trigonoplanar geometry can be visualized as an equilateral triangle with the central atom at its center and the 3 substituents pointed towards the triangle's 3 corners, as shown in the drawing there, B. In a perfectly symmetric trigonoplanar geometry, the angle between any 2 bonds made to the same central atom is 120. Atoms with a total of 2 bonds or lone pairs normally adopt a linear geometry in which the 2 substituents are oriented on opposite sides of the central atom, such that the 2 substituents and the central atom are collinear. The angle between any 2 bonds made to an atom with linear geometry is always 180. The bond angles found in real molecules can deviate from this. So real molecules may have a difference in the bond angles suggested here. Ionic and electrovalent bonding. For ionic bonds to be formed between any 2 atoms, electropositive elements readily give up electrons and are usually group 1 or group 2 elements, as we have said before, whereas electronegative elements like we saw fluorine, which had 4.0, and chlorine readily take up electrons and are typically group 5, group 6 or 7 elements. Ionic compounds in the crystalline state consist of orderly 3-dimensional arrangements of cations and anions held together by Coulombic interaction energies. These compounds crystallize in different crystal structures. Covalent bonding. Atoms of elements in the central groups will complete the outer electron shell by sharing its electrons with the neighbors to form covalent bonds. Carbon, as an example, in its outer shell has 4 electrons. 4 more are required to fill this shell. These may be acquired by sharing an electron with each of the 4 neighbors when carbon is in solid form. This we can see when carbon forms carbon atoms in diamond. All the 4 electrons are shared, forming 4 bonds in that carbon structure of diamond. The 4 electrons in the outer shell act so strongly with one another, that is, they tend to repel, and each electron cloud concentrates itself away from those of the other 3. The 4 arrange themselves with the largest possible angle, which is the angle we earlier on saw with the tetrahedron structure. If it is a tetrahedral structure, then the bond angles are 109 degrees, 109.5 degrees between each pair of electrons or each pair of bonding electrons. Metallic bonding and van der Waals. This type of bonding is confined to metals and near metals, a number of which are found in group 1, 2, and 3 of the periodic table. Those groups that were labeled B, 2B, 3B. We have 2A, 2, 3A, we have 2B, 3B. The positively charged ions are held together by their attraction to the cloud of negative electrons in which they are embedded. The inert gases condense to form solids if sufficiently low temperatures are provided, yet their closed shell configurations have no interaction between one another in the form of formation of bonds that we have already discussed. So we find that in what we refer to as inert gases, neon and argon and others, we say that the kind of atoms there arrange themselves differently. This points to the presence of another kind of bond called a secondary bond, wherein no major modification of the electronic structure occurs. In reality, the electron cloud results from the motion of various electrons. Thus, electrons must be regarded as in motion around the nucleus. Van der Waals forces, by their nature, act over large distances between electron clouds which do not overlap one another. Thank you very much for your attention. We will return with our fourth presentation.